Okay, guys, we're going to start two-body problems now. These are pretty challenging. The most important part of this is to get the free body diagram and then sort of analyze what's in front of you. Now, usually what's going to happen, so just going to get you started here. So usually there are two unknowns. Usually. And they are the acceleration of the system and the force transmitted between the objects. Okay, and I will draw you a picture for this in a second. Or else actually, let's just draw a picture right now. So consider this picture here. You just have basically like a shelf or a table, just basically a table with a bookend. You have a mass on the table connected to a string, and that string is connected to a pulley, and then the pulley switches the direction of the string, and you have another mass hanging on the other end of the string. So the reason it's called a two-body problem is because, well, there's two bodies. Now, usually they're going to have these two unknowns, the acceleration of the system and the force transmitted between the objects. So in this case, the force transmitted between the objects, what connects these objects? The string, and therefore the force is tension. So typical question would be, find the acceleration of the system and what is the tension in the string. So in order to do this, you have to understand free body diagrams pretty well, and you have to understand net force. Okay, so you have to know free body diagrams and you have to understand net force. These two ideas are critical to your success. If you do not understand those, or if you try to skip steps, or if you don't draw these free body diagrams completely, it's gonna feel very challenging. Okay. So do I need to explain what's going to happen with this picture, or is it obvious? The two objects are connected by a string, which transmits the force from one object to the other. So what's going to happen on this? If, say, it's frictionless on a table, what's going to happen? There's no friction on this table. What's going to happen? What forces A down? Obviously, gravity, right? And then that force of gravity pulls down, right? And then therefore the string will pull on the mass. Okay? So the string wrapped around the pulley, let's just at least talk about that. It's the string wrapped around the pulley changes the direction of the force, but not the magnitude. Can I just put meg? Okay, so object A falls downward because of gravity. And this is what we'll put. Just sort of analyze the situation completely. Object A falls down because of gravity. Pulling down on the string. So the tension in the string is created from the downward force of gravity. So it's pulling down on the string, and the string will tighten up and it'll fall down, obviously. Now, this downward force, the direction is changed, okay, due to the pulley, and you're going to end up pulling right on the mass labeled B. Okay, so object A falls down, pulling down on the string. Okay, let's identify exactly what's happening. The low end of the string pulls up on A, the high end of the string pulls right on B. With equal magnitude. Okay, so you'd have like tension going up on A. You'd have gravity a little bit larger pulling down. And then the tension here pulls right on B. And if there was some friction, there would in a realistic situation, you'd have this here. Friction stopping it. And depending on the size of A, depending on the friction of the table, different things are going to happen. Okay? Any questions about this situation? Two-body problem. The pulley changes the direction. That's the big idea here. The pulley changes the direction. Can I go to the next page? Hey. A little bit, yeah. Yeah, grab him. Oh, he should be here. Is Sean here today? Okay. I guess he's not here. I did see him too, didn't I?
He wasn't in my class.
Okay. Okay, next page. Okay, so for these problems, step one, is a system approach. The two objects are considered to be a single moving object. Together as a whole. And therefore you have this mass of the system, which would be mass of A plus mass of B. And this is the most important thing here, is that the acceleration is the same for both objects. So this is the most important thing. So if one of the objects is accelerating at 2 meters per second, the other one also has to be accelerating at 2 meters per second. So the acceleration of the system as a whole is going to be consistent for both objects. Okay, and then step 2 is that you isolate one of the objects. You draw a free body diagram. And then you can analyze the individual forces. Isolate one of the objects. A free body diagram is constructed and the individual forces acting are identified and calculated. And there's some typical questions involved for this, and I'll give you all of them. There's situations where there's just masses hanging on pulleys. There's situations where, like I drew on the previous page, there's situations where there's, you know, a mass connected to another mass connected to another mass with strings, and then you pull that. There's masses connected to pulleys on ramps. So I'll try to give you a couple today, and then I'll try to give you a couple tomorrow. And by far, these are some of the harder problems you'll see in this section. So just let me know when you're ready to go, and we can do a first example. It's called the Atwood pulley or the Atwood machine. As soon as you guys are ready to go. So everybody in here is past 10C, correct? Because we have to do a systems of equations in this stuff. So that's that system approach, almost like the system approach means, you know, the physics system, but it actually has a nice little play on words where we're going to have to use the systems of equations. Okay, are we ready to do this? All right. So whenever you're ready. Which one? Are identified and calculated. It's cold in here? It's hot in here? Okay. So you're going to draw a pulley. You're going to draw mass 1. And then you're going to draw mass 2. Mass 2 is a little bit smaller than mass 1. So mass 1 is going to be 200 grams, and mass 2 is going to be 50 grams. And then just by looking at that diagram, you should identify, or you should be able to identify which way the acceleration is going to occur. Are we going to be, is 1 going to fall and then 2 is going to rise, or is 2 going to fall and 1 is going to rise? And so which one's heavier? So 1 has more mass, so therefore the weight of 1 is larger, so then this mass should fall and 2 should rise. Why not? Okay, so determine the acceleration of the system. And the tension in the string. Okay, so the systems approach. So we said that the pulley, all it does is change the direction of the forces. Okay, so what we can do is we can draw a free body diagram just on one dimension. So draw one connected to two, and now we can draw the free body diagram. So let's just think about which way is one going to fall. Obviously it's going to go like this, right? So we can say that one is going to pull this way, and we can call that FG1. And like, what's going to slow that down? What's the opposite of that? Because 2 also has gravity on it as well, right? Except the force of gravity on 1 is slightly larger. So we can point this way with FG2. FG2 opposes FG1. And what goes on the other side of 1 and 2? So you have tension in the string. And the tension in the string is going to be the same. Okay? You have the tension in the string pulls up on 1 and pulls up on 2. So you'd have, if they were isolated, you'd have an upward force there and it pulls an upward force this way. And then basically these things are equal opposite and you don't have to worry about it. They cancel. In this situation, for sure. Let's just deal with one thing at a time. So your F net will be FG1 minus FG2. And I always just start with the bigger one. So for your F net formula, this is the most important step aside from the free body diagram. Put the larger force first. Okay, so now we can go ahead and solve this. So remember in the formula sheet, right? F net has two forms. So on the left side we put MA, and on the right side we have the sum of all the forces involved. In this case it's just 2. So we go M1G minus M2G. And we got to be careful about this M right here. Which M is this? Is this the mass of 1, 2, or both? Oh, you guys are good. So put a little T there for total, M total. Okay, so if you look back in the notes, the very first thing I started with, step 1, what does it say? System approach, the two objects are considered to be a single moving object together as a whole. We have the mass of the system. We've done this, we've used mass total, and then the acceleration is the same for the system as that of the individual objects. So we need to solve for the acceleration. So we need to solve for this. So we're going to divide out the mass total. Anything on the right that could be factored out? Factor out G, and you have M1 minus M2 all over mass total, which we could change to mass 1 plus mass 2. You guys okay with that? And then there's your formula for the acceleration. So we have 9.81. We have m1, so 0.2 minus m2, 0.05, all over 0.2 plus 0.05. Any questions about those decimals? Because we started in grams, right? So we would have to divide by 1,000 to get to kilogram. So go ahead and punch this into your calculator. So please double check that you know how to punch in expression that's got brackets and fractions and stuff. So double check that you have the same 5.886 as myself. So just going to give it about a minute to make sure everybody's got their calculation. Any questions so far? Okay, and I'm not too worried about sig digs at the moment. Now what we're going to do is step 2. What does step 2 in the notes say? Isolate one of the objects, and then a free body diagram is constructed and the individual forces are identified and calculated. So let's pick one of the objects. Which one do you want to pick? One? All right. Switch back to the black ink. Okay, so let's just take a look at block 1. FG1 is pulling it down, which we just changed to left. And what's on the opposite side of that? The tension. And the tension force has to be smaller than that FG1 so that it pulls it down. So we need to do a net force equation for this free body diagram. Okay, so just like this net force equation went with this free body diagram, we have to come up with another one. So what's the net force on this body? Fg1 minus T. Good. And what are we trying to solve for? Now that we've determined A, we need to also determine the tension. So how to solve for the tension? Bring the T over here. Let me just go back to blue. Bring the T over here, and you'll have Fg1 minus F net. So Fg1 will be 0.2 times 9.81 minus F net, which is 0.2 times 5.886. So just before we calculate this, why did I use 0.2 for the net force? How come I didn't use 0.25? Good, you're only worrying about this. So like this formula here is, and the F net here is separate than this F net. This is the F net for one body. You can, yeah. Yeah, you could do something like this. You call this one F net 1, 2, and this just F net 1. However you want to do it. Okay, so figuring this out, we get 0.2 times 9.81. And over there, 0.2 times that 5.886. Subtract the 2, and you should get 0.7848. Okay, so we have the tension, and we have the acceleration. And this is the free body diagram systems approach. When you look at it as a system, and then you look at it one at a time. Now I'll show you a simpler way, if you're good at math. If you're good at math, there's a simpler way. This is a very good example though, because it gives you an appreciation of how to use the free body diagrams and the FNet formulas. So let's try the exact same question with a little bit different technique. Okay, so if we were to look at the two masses separately, did I call them mass 1 and mass 2? What we can do is we can do a free body diagram separately. So this would be the systems of equations approach. So it's weird because like in the physics they call it a system because it's like a two-body problem, so like the mass of the system. But and then in math they have the systems of equations, so you can't get confused by that system. They're not connected. It's just a coincidence. Yeah, it's just a coincidence in names. So if we consider each body individually, then what we can do is create a system of equations, because there's two unknowns and you have two sets of information. So what's going to happen on mass 1 gives you certain amounts of constraint, and then what's going to happen on mass 2 is another certain amount of constraint, and you have so two sets of information and there's two unknowns. So like in math, if you have two equations and two unknowns, yeah, you solve them. Good. So that's what's happening here. Okay. So let's take a look at mass 1. What was happening on mass 1? You had a force due to gravity, and you had a tension force. And its acceleration is down. And the force of gravity, I'm just going to go ahead and calculate it really quickly. It was 0.2 times 9.81, and you get 1.962 Newton. And for mass 2, which also has a force of gravity, that's Fg2. So that one was 0.05 times 9.81, and you get 0.4905 newtons. But its acceleration is up, so this tension force is going up, and it's the same size as that other one, so it's just... So the tension's the same in both. The acceleration's the same in both. So you have your unknowns that are the same for both, and then you have two situations. Oh my gosh. Two situations which are basically like your two equations. Okay, so let's get them down. So for the first one, you have F net equals, which one's larger for the first one? So you go Fg minus T. Yep, this is equation 1. Yep. yeah, you're going to have basically like this. So what's the other one going to look like? F net is going to be, which one's bigger? T, because it's going up. So on this side, you'll have T minus FG2. So then you can just treat it like a math problem. Okay? So we just punch in what we know. So for the first one, the net force, which is MA, is going to be 0.2 A. And FG1 we know is 1.962 minus T. So you can think of it as like Y and M, and for like Y equals MX plus B, it's like Y and X. Remember those from Math 10? So think of this as like your Y, and T is like your X. It's just like math class now. Now on the other side, you have 0.05 A T minus 0.4905. That's the weight of the second mass. It's just the kilograms times the acceleration of gravity. So now we have two equations, and we're going to make a system. So you guys remember solving systems? What do? You got to stack them in columns and then eliminate, or you could do substitution. So I like to just stack them in columns. So 0.2a equals 1.962 minus t, and then the other one will be 0.05a. And I'm just going to reorder the right-hand side so that they are stacked in columns. So negative 0.4905 plus t. And then what you have here is a systems of equations that, and this will always happen where there's no coefficient on t. So you can typically just eliminate t quite easily. How would we eliminate t quite easily here? Yeah, which one? Are we going to add these equations or subtract these equations? Eliminate t by adding. So that's like in math class where you do an elimination method. So let's add. You get 0.25a. The t's cancel, and you have to add those. So what do you get? One point 1.4715. Good. And now we have to isolate a, so divide out 0.25, 0.25, and then you've solved for a. And you get the same thing. And then just like in math class, once you find the one variable, you got to go sub it back into one of the equations and get the other one. Okay? So I'm just going to sub this back in. I'll just choose I'll choose the second one. I don't know why. I will. So subbing back in, 0.05 times 5.886, and then I'll plus 0.4905, and I'll have the tension. Which one do you guys like better? What's it called? Like a two-body system approach. So this one's like more for like the math keeners, because you can just, you think about them separately. This one's separate than this one. You get the two equations. And then the first one is more of like a physics sort of approach. Okay, so let's go to the workbook. And we're gonna go slow and steady on these questions, okay, people? Because they are challenging. Okay, so it's in the workbook where you left off the homework. It's just after question 14. All right, so if you take a look, it starts here. But I don't want to look at 15 right now. I want you to try 18 and 19. This is your homework. 2 questions. Okay, you are on your own. Okay, if you need to quietly talk to the neighbor for assistance, that's fine. If you need to talk to me, that's also fine. But this is your homework for today. 2 questions.